Alright folks, this video is for my college algebra colleagues on module 2B. What I think we could play with here is, as we're introducing functions, first off, that's a function and we should let them know that. Let's call it, I got some in Desmos here. Boop. You know, we could have used this, right? You have to use the plus sign. It's weird because there is no other, like, it's so fundamental to humanity. But anyhow, this could be used for addition, and then let them know that multiplication is a function. We could have called like m's. Oh, come on, keyboard, don't fail me now. Oh, come on, m there. M sub 3 could have been the name of the whatever your input is, multiply it by 3 function, and we could have had the m sub 4 function. You know, I try to tell them to forget about division and subtraction. You're adding a negative or multiplying by a fraction, and of course you could have a m sub 1/4 boop, 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 it's equals x times 1/4, of course. But it turns out, oh, it doesn't like that. That's okay, because you know what? We could also label it boop, 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 m sub 4 inverse. Booyah. Let's make these go away. Touch screen. Pow, 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 pow. I have very little time, so I got to get through this quick. Oh, I need an X there. Silly goose. Right. All right, so we're trying to get them through composition of functions. We got them addition. Repetitive addition is multiplication. Repetitive multiplication is exponentials, and they have their notations. And if we use function notation, things would be great, because they know how to multiply a number by itself. They just don't know what the input is. So instead of having that arbitrary notation, they wouldn't have any of these problems. We used this guy. And that function is multiply times itself, right? And I shouldn't, this is totally wrong. M sub 4 should be this. Everything is in definition of addition, okay? That's what it should be, and this should be this. Oops. Because addition is something that where you take 2 piles and throw them together into one pile and rename it, is all that really is. Okay, so you get it. So if you wanted e sub 2 of 3 or negative 3, they wouldn't have any of these problems. All these problems they have in arithmetic is because of how we choose to do our notation. It's not because anything's wrong with their brain. We just haven't evolved the notation to be unambiguous and precise and concise at the same time. So, but nobody wants to type m sub 4, or I hate to say type, write m sub 4 of x when we could say 4 times x, right? That dot is great. 4 times x. It's so convenient you can even leave it out, okay? Now, we build up to the, you know, this kind of notation, right? That's the name of a function, that's the name of a function, whatever. And we do things like, oh, well, what if this is equal to that? Okay, and then what if this? And the order, when does the order matter and when does it doesn't? Pizza on pineapple, pineapple on pizza. I try to use put your makeup on, wash your face, put your makeup on, and results wrong. And before we get here, I try to, well, actually after we get here, I say, can you find the cheesiest examples of when this happened? Well, first I try to do this, where they find where they're just equal for a number, right? And then I go to the next case where they're equal for all. And then I ask them cheesiest versions. And I'm hoping they will be like, well, when G is the same as F, right? When they're the same function. That's the cheesiest example. You got to hit the bottom cheese first, okay? Then I try to get them to think, are there any other like special cases, classes of functions? And I'm hoping that they'll realize that I'm trying to lead them, since these are commutative, our only three operations we need to know are commutative, that if the functions are of any of these, what is it? Whatever, the squaring function versus cubing, you can, this guy, you can cube, square, or there you go, that guy. You know, our basic, this is just repetitive addition, repetitive multiplication, and multiplication is repetitive addition. It's addition all the way down, right? Of course, the abstract part of it, that's how we invented it. The abstract part is when we use the concept of number and we put a number that we know up there. How can we think of that as like multiplying 2 times itself half the time? That's when the abstraction comes, okay? And these are the things that is the reason why we can have a PlayStation controller and press buttons, and we don't have to yell at the computer 0 1 1 1 0 1 1 1 1. And that's the power of it. But anyhow, back to this. So yeah, if the functions are just a simple one-step operation using any one of the 3 action buttons that we know how to use: addition, repetitive addition, repetitive and repetitive addition, because these are commutative, then these will be commutative. But then we give them this guy. This is what I want them to see. All right? Sure. This is a special case, okay? Because, yeah, these are just addition. Oops, whatever. Command Z. This is what I'm trying to get them to see. Yeah, this is one of those where you're just adding a number, but this is a special case of just adding a number. It's not just any number. This could have been a 5, and this would have been true. I'm trying to lead them to see that this isn't just this. We've been focusing on, is this equal to that? Is this equal to that? Is this equal to that? And this happens to be a case where this is equal to that, but it's a door into another world. The fact that the output, which we haven't even focused on, because we've only been focused on that, is this, which is the do-nothing function, the identity function of functions. All right, it's home base for functions. That's what I want them to see. And realize, oh, inverses have this property, and this, because our favorite relations, and here's the other thing we do. We have these arrows, right? We could just put the bar, boop, boop, it's a relation. Everything else is artificial. To say arrows, we're implying input and output. To put arrows, we're implying input and output. To put an X and Y, we're implying input and output. And for this inverse thing, here's a glimpse of what I learned. All right, here is this guy. If you want to find the inverse, do this. That's the graph of the inverse. Cool, but you know what? I don't like my x's up and down, and that's just, I'm not used to that. So what would I physically do to that thing to fix it? Because this is the inverse. It's the inverse of this guy. That's it. Right? But there we go. That's the inverse. Well, to fix it, you'd have to pick it up out of the paper and put this where you want it to be and put that where you want it to be. And if you did that, you'd have this. I want them to physically, imagination-wise, do that so that they realize it's not something they've memorized. It's the same as flipping it over the diagonal. So I want them to think in their brain and have the actual physical neurons that would be your arms, so that it just becomes obvious instead of a memorization thing. That gives us that opportunity. All right, so from there, we have opportunities. Every function, no matter how insanely crazy it is, whether it's something like, look at this crazy mess, it's so much. I want them to realize it's 4 little bitty functions. Just like this is more fingers than I have on both hands, it's really a bunch of little finger piles. Okay, we like that. Oh, I don't know how to use this yet, but I like the whole what is F and G thing, but the question we're asking should be, how many different choices do we have for F and G? Oops. That's a better question because it lets them play and think, okay, instead of pinholing them. So I like to show them, what are the action buttons? Multiply, add, and I don't call that the 1 over. I call that the flip function. Why? Because if you do 1 over, sure, that goes to this. But what if you start off with this? Then 1 over is that, and they hate fractions, and this is a 3-story building of misery. No, it's better to think of it as the flip function. Because when you flip that, you get this. And if you flip that, you get this. So the flip function is its own inverse. Ooh, and it also helps to avoid these hierarchical piles of awfulness. All right, we don't divide by 2, we multiply by a half in this land. There's no such thing as division. Now, so I like to say, if you do things, you just have to do them in the opposite direction. Now this is key. I kind of like this because I could say the first thing they did is multiplied by 7. The second thing they did is subtracted 8. So if you put that there, you get this, right? And then the third thing they did was the flip function, flip. And then the fourth thing they did was cube root. So you put that there, and then put that there, and then put that, and then I show them, it's like, okay, I had a number. The first thing I did was multiplied it by 7. The next thing I did to that output was this, and you get the drift, right? Okay. So how many different choices do you have for F and G? Okay, fine. You can pick this for F. Well, I'm sorry, it's backwards. That one for G, and this one for F, that one for G, and, this one for F, this one for G. So you have 4 different choices. That's the answer. Woo! I want them to tinker with that. But also, I want them to recognize that this is the name of a function. This is the name of a function, the same function, but this name has built-in instructions that tell you the output for a given input, but it's still just a name. This is 4 functions inside of one another, but sometimes we choose to write it like this. This is the name of the same function, but this name, unlike this one, which gives you instructions that give you the output for an input, this name tells you which functions are composed to give you that. This one's quick for referencing. This one is good for referencing in a different way, has its own use, but these are all just names. The function itself is a concept. It's the relation. If you graph, is this the graph of the function? No, this is the collection of inputs and outputs. It's not even all of them. We could have plugged in complex numbers, we chose not to. So the domain we choose is also an artificial construct, okay? And the function, we don't have to plug in anything into it. Every function's invertible if you don't plug anything in, right? Nobody said I had to put input in. I could pick this, that, and you know what we're talking about, the restricted domain. I'm just trying to show them that the function is an idea in and of itself. All these things are just representations, right, that we use because they're useful tools. So I like that, but I also want them to see, oh, I can just look at this and I can write the inverse down. What would the inverse be? I give it this name, right? Opposite things in the opposite directions. You're like, oh, okay, cool. The first thing, I'd have to, opposite things, opposite directions. So I need to, that's the last thing they did, right? So I'd have to cube it and then do the 1 over thing, and then I'd have to do the plus 8, and then I have to do the undo times 7, which I hope they do that and not this, because otherwise they haven't been listening. And then, of course, prove. that they are inverses. Great. And that's a nice logical trick, but then I mess them up. Isn't that cool? You don't even have to do math. Turns out, whenever you're like working a problem and it seems like you're just thinking, that's when you're doing math. If it feels like you're doing math, that's not math. That's computation, a thing a dead computer can do. I mean, technically, mathematicians invented it to do part of this stuff. It should be a lobe of our brain and accessed at any time. But anyhow, then I'm like, all right, cool. You like how that works? Finding the inverse is so easy. And then I'm like, hey, what if we have this? You know, okay, cool. Try to apply that trick. And then it breaks. You can't. It's not sequential because of that. Boom, what do? Well, every relation is invertible, right? And who cares? This is really is a relation. Who cares that it's a function? I don't care. You know, we can invert anything. And of course, it's not really two methods. You know, switching the letters and then the thing. That's trivial, right? They should be able to see through that. You know, they are actually humans that are alive with brains, and if we let them think, they actually will. We don't want to waste all their time competing with the computer. But anyhow, the problem is algebraically, you know, if you do the old switcheroo, I'm like, hey, there's two different y's. But if we are going to make this a function, they always look like this. One y and then x's. So we need a little algebra trick. And it's not something you need to memorize. I bet they could creatively figure it out if they viewed it as any problem they've ever solved in their life. Well, first off, how do I do that? This only has one y. I don't know how to do that, but you know, this thing over here, these are different. If you want to make them the same, first identify the differences. This does not have that on a y on the bottom of the bar thing. Maybe I could fix that at least. Okay, they could do that. That's not too much of a leap if they had time to play, like if they had those 12 years of K-12 back, you know. Okay, well now the problem is I still got two of them. This one only has one. Now, if I stand a chance of like getting these two together, at least I can get them on the same side of this thing, right? Okay, cool. I'm going to do that so that at least they're on the same side of the equal sign. Okay. And then, well, actually, before I let them do this, I show them, y'all know this is really just this. Again, what do we have? Exponents, multiplication, and addition. Those are the only three things you need to know how to do, and it's really just addition all the way down. Look at that. 1y with the power of that. Here we got 2y's with the power of this operation. But when you go down to the actual addition, which is really what it comes down to, not only do you have 2y's, but you have two different powers of y's. Ew. This connection, your three operations, give you that leeway. That's your tool, your path. All right. So here, they might see that, a sum to a product. 1y, and this is just a number. Now you might think they can't do this. They can do this if we let them actually think. Let them think. Quit forcing them to know stuff. It's literally Cartesian coordinates. I think, therefore I am. It's what it means to be alive. The brain does it whether you want to or not. And forcing them to compete with the computer is literally torture. It's not only preventing them from learning what we want them to learn, it's giving them brain damage to where they can't think even if they're given the chance. Luckily, it's temporary, and I do have some solutions for this issue where we actually to spend less energy than we are now. And it's not changing anything anybody has to do. It has to supplement what we're already doing in the same way. If we supplement it just right, we can invert this doomsday for humanity, because we're just brainwashing people into becoming circles instead of spheres. Okay? But anyhow, I wanted to share that. Oh, I lost it. I make all my students make an account and do this so that they never have to type the quadratic formula ever again. You know, if you did it all day, every day, you'd remember it. But the brain is very forgetful. In fact, that's its job, is to forget. It filters out information, and then its job is to forget. That's what it does. We're terrible at what the computer does. We need to use this. Mathematicians invented computers to do the tedious part, the non-thinking part for us. It's still part of a thought, but it's the dead part. We need to embrace that. We need people that can program the AI. We need to stimulate creative, abstract thought, not crush it. Okay? All right, that's all I got for now. I can't remember the rest. I had to get it out one way or another, so I don't know. Hopefully it helps. Thank you, y'all. Love you.